Hi, everyone. So today we are going to be talking about strong and weak acids and bases. So, strong acids and bases are things that are going to completely dissociate or break apart in water. Some examples of these are hydrochloric acid or sodium hydroxide. So, when these things are put into solution, they completely dissociate. So, we don't have any HCl still sticking together or any NaOH sticking together. These don't have an equilibrium because those ions, like in hydrochloric acid, the H plus ions and the Cl minus ions, those aren't going to come back together to form HCl in solution. So we're just going to have the ions in solution. So there's no equilibrium here. Now, if we want to find the molarity of the H plus ions and the molarity of the hydroxide ions, like if we're trying to find pH or POH or something like that, then all this is going to be is the molarity of the acid multiplied by the number of hydrogen ions we have in that acid, or the molarity of the base times the number of hydroxide ions that are in that base. So this just depends on if it's, a monoprotic or diprotic or polyprotic acid, or the same thing with the base. So if you have a different number of hydrogens or a different number of hydroxides other than one, then you have to make sure to multiply the molarity of that acid or base by the number of protons or hydroxides to get your actual molarity of those things if you're, needing it for another calculation. Now, on the other hand, when we had weak acids or bases, it's not that simple to find molarity, okay? Now, the reason for this is that weak acids and bases only partially dissociate in water. So most ions are actually sticking together rather than breaking apart. So because of this, there is an equilibrium here. So an example here would be like hydrofluoric acid. When we put this into water, some of this is going to dissociate into the fluoride ion, and then that hydrogen ion will then form, add to water to form the hydronium ion. But then some of these things are still going to be reacting together and going back to form these two things. So we have an equilibrium. And another way you can write this is just with the hydrogen ion and the fluoride ion. A lot of the time we will write the water in it as well, though, and the hydronium ion. But again, these two chemical reactions can kind of be used interchangeably as well. And then also here's an example of a base. We have our NH3 and in the water, and then it's going to form NH4, our ammonium ion. Notice how the water here is kind of acting like a acid. It's donating a proton to our base, and we know that that's a base because it is accepting that proton. And then we also get hydroxide in the solution. So this will help us find our POH eventually. And you'll see I have a couple examples that we're going to do today. Now, the equilibrium expression, just like we talked about the equilibrium constant last unit, we have a Ka and a Kb for our equilibrium constants for acid dissociation and base dissociation. So what these things are going to tell us is they are going to tell us the relative amounts of products and reactants, right? We've talked about how since K is products over reactants, when we have a bigger K value, we have more dissociation here because our products are our ions. So again, the bigger the K value, the more dissociation there is. And like I said, it's because there are more products, so that acid or base has broke apart or dissociated more. So when we have a large K, that means that that's a stronger acid or base. So remember, strong acids and bases, I had that on the last slide, they completely dissociate. All right. There is no, acid HCl that is together anymore. They're completely broken apart. So when we're talking about weak acids and bases, we have a equilibrium constant, and the bigger the equilibrium constant, the stronger that acid or base is. And that's very important to remember. All right, so let's do an example here. I have two examples. I'm going to put myself in this corner just so I block the just example. And so my first example is, what is the pH of a 0.05 molar solution of acetic acid? I'm also given a equilibrium constant for the acid dissociation here. Okay. Now, what I'm giving you here is the initial molarity or the initial concentration of acetic acid. So I have a couple steps here. our first step is we are going to write the dissociation reaction. And when I'm talking about a dissociation reaction, it is either this acid or base put into water. All right. So we write that reaction, and then we're going to write the K expression. We are going to create an ice table because remember, this is equilibrium. So we are creating more ice tables this unit. And then we are going to solve for pH or pOH, whatever we're being asked for using equilibrium values. We usually want pH because, usually pH is the thing that we're measuring acidity with. So let's go through this step by step, and I'll show you what I mean by each step. So first and foremost, we're going to write the dissociation reaction. So like I said, we're adding acetic acid to water, and then because this is an equilibrium expression and this is a reversible reaction, I have the double-sided arrow, and then I also want to write my products. So this right here is acetic acid, and I'm adding it to water. Now acetic acid is an acid, so it's going to donate its hydrogen. It's going to donate its hydrogen to water, so I get the hydronium ion, and then I also get my acetate ion. Okay, so that's my first step. Now notice how my acetic acid, my hydronium ion, and my acetate ion, those all are aqueous, right? Now water is a liquid. This is pure water. So because of this, I'm actually not going to include it in my ice table, and I'll show you what I do with that a little bit later when we actually create our ice table. Now let's look at step number 2. We're going to write our equilibrium expression. So K equals products over reactants. And remember, I only include aqueous substances and gases in an equilibrium expression. So that means I also do not include this liquid water in my equilibrium expression. So I have my products, my hydronium ion and my acetate ion, and then I have my acetic acid on the bottom because that is my only reactant that I am including. Now, the next step here is I want to create my ice table. So I have my initial change equilibrium, my ice table. And like I said, I am not going to be including my liquid water in my ice table. So I just like to put a big X through it in order to just remind myself that I just do not even include that. So now with our given information, let's fill in our ice table. Now I know that my acetic acid initial molarity is 0.05 molar. So I'm going to put that in the initial row right here for my acetic acid. I don't initially have any product because I'm putting this acetic acid into the water. So I put 0, 0 there. I know that I'm going to lose some of my reactant. I am going to gain product, and all of my coefficients are 1 here. It's a 1 to 1 to 1 ratio, so I have 1x in all of those. And now the next thing I do is just add downward. I get 0.05 minus x for the equilibrium constant for acetic acid. I just get x for my equilibrium constant for my two products. So I'm going to bring this whole table over to the next slide. Okay, so next step here is we want to bring our equilibrium expression over to the slide as well, and then we're just going to plug in all of our givens now. So remember, my equilibrium constant K for this reaction is 1.8 times 10 to the negative 5, and then I have all of my equilibrium concentrations. So now I can plug that all in here. So I get K, which is 1.8 times 10 to the negative 5, equals x times x, because those are my two equilibrium concentrations of my two products, over 0.05 minus x, because that's my equilibrium concentration of my acetic acid, my reactant. So now it's just math, right? I'm going to multiply these two things together to get x squared, and then I'm going to multiply both sides by this 0.05 minus x, like this, in order to get rid of that on the denominator. And then my next step here is I'm going to distribute this 1.8 times 10 to the negative 5 to both the 0.05 and the negative x. So I do that, and this is my next step. Now, I know that I have a quadratic here. I have an x squared, I have an x, and I have a term with no x. And so I need to get it all on one side of that equals sign. I personally like a positive x, so I'm going to move it all over with that x squared. So I'm going to get x squared plus 1.8 times 10 to the negative 5 minus 9 times 10 to the negative 7th equals 0. So now I have my A term, my B term, my C term, and now I'm going to do the quadratic formula. So I get x equals negative b plus or minus square root b squared minus 4ac all over 2a. And I have a beautiful singing voice. You don't have to tell me. So next step, I like to do everything under the square root first. So I put this into my calculator, 1.8 times 10 to the negative 5 squared, and then minus 4 times 1 times a negative 9 times 10 to the negative 7th. And then when I have this in my calculator, then I like to do like square root of the answer, if you know what I'm talking about. If you don't know how to do that in your calculator, I can show you, or you can just do it step by step, do everything under the square root first, then take the square root of that number, but you end up getting 1.9 times 10 to the negative 3 for all that. Now we do our plus or minus, and then we divide by 2, and we get two answers here. So I get 0.0094 and a negative 0.00096. So we have to think about these answers, right? Because we don't want one of them. We're going to throw one of them out, and we're actually going to throw the negative one out, because notice how my two products are both X. And remember, this is a concentration here. So I can't have a negative concentration. That doesn't make sense to have a negative concentration. So that's why we throw that negative number out. So now I know that X equals 0.00094. And remember, the whole point here was that I wanted to know the pH of this solution. Now, X here is giving me the concentration of the hydronium ion. So from this and from the equations that we learned the other day for pH, I then can solve for my pH because I know my concentration of H+. So I know pH is equal to negative log of H+, or negative log of the concentration of the hydronium ion. So just plugging in my 0.00094 for that H3O plus, we end up getting 3.03 for the pH, and that's my answer. All right. So you already know how to do this, right? You already know ice tables. You learned about pH calculations the other day. So now we're just putting all of that together. And this all obviously is a acidic solution because it is a solution of acetic acid. So let's do one more example. My next example here, it says, what is the pH of a 0.34 molar solution of methylamine, so CH3NH2, if the Kb, or base dissociation constant, is 3.7 times 10 to the negative 4. Now remember our steps here, okay? We're going to write our equation, our chemical reaction. We're going to write our equilibrium expression for Kb, and then we're also going to draw an ice table and do that ice table first before we can even solve for anything relating to the pH. So first step here, I write my base dissociation equation. Now, if you look at that methylamine and you're like, what the heck is that? Right? This is a base, okay? Remember, acids have H in front of them. They're very easy to spot. But bases are not always so easy to spot because they don't all have OH, right? This one doesn't have an OH. So because of that, we can see that this, since it's a base, and this will clue you in also that Kb means it's a base dissociation constant, but this right here is actually going to be receiving a proton from water. So since it's receiving a proton, that means it is a base. So here is our chemical reaction. We have our methylamine plus water, again, liquid water here. And then we receive that proton from the water, and we also have this hydroxide from the water because it lost a proton. Okay, these things are all aqueous, and then our water is liquid. So if we draw our ice table, we now can put this 0.34 molar in for our initial concentration of that methylamine. Again, I cross out the water liquid because it is pure water. It does not have a molarity. So I don't have any product yet. I put 0 and 0 in my initial quantities for product. I know my change will be, since it's a 1-to-1-to-1 ratio, it's just going to be minus X for my reactant because, again, I'm losing reactant to make product. And then it'll be plus X and plus X for my two products. And then I just add downward for my equilibrium constants here. I get 0.34 minus X and then 0 plus X for both of those products. So base dissociation constant, remember, we do not include liquid water because we don't include any liquids or solids in our equilibrium expressions. So we get that the K is equal to my two products. So concentration of this times the concentration of hydroxide over the concentration of my methylamine, my reactant. And so plugging in all of our numbers that we know here, we know the Kb is 3.7 times 10 to the negative 4, which you can also write like this. Remember that negative 4 just means I'm going to move that decimal 4 times. I'm moving it over to the left 4 times from that where it is inside of that 3.7. So that's another way to write it. Scientific notation is just another way to write a number. Okay, so you could write it like this too if you want. And then I get my concentrations, equilibrium concentrations of my two products. So X times X on the top, on the numerator. And then I get my equilibrium concentration of my reactant on the bottom. So 0.34 minus X there. Same thing here. I'm going to multiply both these x's together to get x squared on the numerator here, and I'm going to multiply both sides of this chemical reaction of this equation by this 0.34 minus x in order to get rid of the denominator and bring everything up to the same level. So I get this, and then now I'm going to distribute that 0.00037 to both the 0.34 and then minus x. And so I get this when I do that. And then again, I have a quadratic, so I'm going to get everything on one side of that equal sign in order to do my quadratic formula. So again, I like a positive a term, so I'm going to get everything over with that x squared. So I get plus 0.0037x minus 0.000126 equals 0. And then we do our quadratic formula again. I won't sing for you again. I know you're probably getting sick of it at this point, but this is what our quadratic formula looks like. And then again, I'm going to bring it over to the next slide, and then I'm going to do everything under the square root first and then square root that thing, and I end up getting 0.0225 for this whole mess right here, okay? So now we do both our plus and minus, and then we divide by 2 for both of those things, and I end up getting 0.011 and negative 0.0114. Again, because I have just x right here and just x right here, I can't have a negative x because I can't have a negative concentration. So I throw that one out, and so I know that x equals 0.011. Now, this is not my answer because remember, I want what is the pH. So we can't just do negative log of this x now because you have to think about what am I getting here? X here is equal to the hydroxide ion concentration, not the hydrogen ion concentration. Okay, so this one's a little bit different because it's a base dissociation. So because my X is equal to my hydroxide ion concentration, I can find POH, not pH right away, but I know that I can find pH from POH. So that's a two-stepper here. So I get POH equals a negative log of the hydroxide ion concentration. I know that my hydroxide ion concentration at equilibrium is this 0.011. I just got that from all of that math I just did. So I'm just going to plug this in for my hydroxide ion concentration here. So I get negative log 0.011. Plugging that into my calculator, I get that the pOH is 1.96. And I know from one of the other equations that we learned the other day when we talked about pH, that pH plus pOH equals 14. So now with this equation, I can just solve for pH. So I know pH is going to be 14 minus pOH, and then plugging that 1.96 into my pOH here, I get 12.04 for my pH. So this makes sense because this is a base dissociation, so it should be a very basic pH, right? A basic solution. So that is how we do calculations for weak acids and bases. Again, I said this before, but notice how you are not doing anything super new here. You already know how to do ice tables. You already learned about your pH calculations. So now all we're doing is we're bringing those two things together and we're applying them in a different way. Good luck on your checkpoint and let me know if you have any questions.